Good afternoon, everybody, and I hope everybody is okay, taking care of yourself. And today we have another seminar, and we have a guest that is Samuel Hadden. And Samuel has a degree in physics and maths from the Purdue University, a PhD in physics and astronomy from Northwest University, and some postdocs, and now he is a postdoctoral fellow at the Canadian Institute for Theoretical Astrophysics. And today, Dr. Hadden is going to give a talk on celestial mechanics with the celmech code. So it's a new code that we found it to be very interesting, and let's see what you have to show to us. So the podium is yours.
Great, thanks. Yeah, so I've really tried to organize this talk as basically just a tutorial on how to use this new code, celmech. So I really encourage anyone with questions about, if you see something in the tutorial that you want to know more about, I'm more than happy to sort of pause and go into more depth on that. I've sort of organized everything in this sort of Jupyter slideshow. And have actually the notebook running in another window, so if you want to sort of take a detour and see something in the notebook in more detail, please, by all means, interrupt me and feel free to stop me and ask questions. And I'm happy to go into anything that people want to see more about. As it stands, my plan is to basically go through some examples that sort of illustrate how to use this code and what it's good for. So I'll go ahead and begin. Yeah, so this is a new code that I've worked on with Dan Tamayo, as well as some contributions to other parts by David Hernandez at CFA a little bit. So what is the code? It's basically a code for all sorts of celestial mechanics calculations. In particular, one of the sort of core features is that it can calculate disturbing function expansions using some algorithmic details that are sort of under the hood for doing disturbing function expansion to any order you might like. And it combines that ability with the ability to sort of construct, manipulate, and integrate any sort of Hamiltonian equations of motion that you can put in. And then there's lots of other sort of little bells and whistles in there as well. It's a Python code, so the user interface is entirely Python, and it's developed mainly in Python as well. And one of the core design features of the code is that it's designed to work closely with the rebound n-body code. So if you do n-body simulations and haven't tried out the rebound code before, I strongly urge you to. It's a great code, really robust and fast, as well as having a really easy to use Python interface. I've been able to get all sorts of undergraduate students up and running n-body simulations with it. So it's designed to work closely with rebound, and it also takes advantage of a lot of symbolic mathematics capabilities that are part of the SymPy package, which I guess you'll see some of the symbolic mathematics capabilities throughout the tutorial. Okay, so that's what it is. Where is it? So it's on PyPI, meaning you can install the code with a simple pip install celmech command on the command line. That'll install the code and all the requisite dependencies. If you really want the sort of bleeding edge development version, you can check out the GitHub repository, which also includes a lot of Jupyter examples. So I'll just show what that looks like. So it's on GitHub, like I said, and there's a folder of Jupyter examples that demonstrate all sorts of features of the code. So I think this is usually the best way to learn to do something new with the code, is to just check out one of the examples. I'll just click on one at random to just give you a sense of what these look like. They're just Jupyter notebooks that you can copy, follow along with, modify, so that each one does something different with the code. Okay, so in addition to all those examples, we've tried to make fairly extensive documentation as well. So this is what the documentation page looks like. And you can check out information on different modules of the code under these different subheadings on the left. Just one thing I'll point out is that if you go to most of these modules, in addition to sort of explainers and text, usually at the end I've tried to put an API that's sort of automatically generated if you want sort of the gritty details of how different functions or classes are implemented precisely in Python. It describes arguments and return values for all the functions. And I've also made this notebook itself available on GitHub. I think Ricardo was able to word along the link, but I'll just say if there's anything in this notebook that you want to see run for yourself and modify, you can just go to my GitHub as Hadden, and it'll be under celmech tutorial. Okay, so it's sort of the top line details of the code. Just go into some of the basic principles briefly. So in-body codes like rebound generally integrate equations of motion directly for some planetary system or in-body system. So that means that they're updating positions based on velocities and updating accelerations by just summing over the pairwise gravitational force between all the bodies in a given system. And there's sort of algorithms that are well adapted. Planetary problems like the WH-fast method, but they're all fundamentally solving some differential equations like the one shown here. So by contrast, celmech works, instead of with direct equations of motion, works with approximate equations of motion, usually derived from disturbing function expansion of the Hamiltonian for the interaction potential, basically, between pairs of planets and powers of eccentricity and inclination. Fundamentally, what you're doing is you're taking the pairwise interactions between individual planets in a system and rewriting them as this multiply infinite sum of cosine terms. And of course, you can't put infinitely many cosine terms in an actual simulation or set of equations. So generally what you do is you just select a subset of cosine terms that you expect to be dynamically important and include those. Okay, so celmech formulates equations in canonical action angle variables, which I'll show in a little bit. And the principal advantage of this approach, or advantages, I think the first most important one is that it often allows you to develop some theoretical insights and simplified analytic models of some dynamical phenomenon that you're trying to explain. And another side benefit is that in some situations it can be potentially a lot faster than integrating a set of in-body equations directly. So maybe that was a little bit abstract. So I think maybe the best way to understand this approach and how it's implemented in celmech is to just look at an example. So I'll start with this example of a two-planet system. And we'll put a pair of planets near a 3:2 mean motion resonance. So here in this block of code, I'm initializing a rebound simulation. So I said celmech is designed to work closely with rebound. So I've just initialized a pair of planets near a period ratio of 3:2. So I'm setting their periods here, giving them some modest eccentricities and setting them up. This orbital configuration. Okay. And so we can take our rebound simulation and use it directly in initializing our celmech model. And so what I'm doing here is sort of creating two instances of celmech classes. These are Poincare and Poincare Hamiltonian, which I'll describe in more detail in just a little bit. But the point is, we just pass our rebound simulation directly to this from simulation initialization method. And we get our celmech model, and we also get our Poincare Hamiltonian piece by passing along this Poincare particles object. So what are these objects? So this first one, this Poincare particles that I've initialized here, is a class for representing planetary systems in terms of canonical variables. So the canonical variables that it sort of natively stores are these shown here, which might be familiar to some of you who've done this sort of thing before, but basically this big capital lambda is related to the planet's semi-major axis, or semi-major axes. Here lambda is the mean longitude, or rather, mean longitude. And then there's these eccentricity-like variables, like we call eta and kappa, and some inclination-like ones as well. So they sort of scale with the eccentricity and carry along an argument of here omega is the longitude of periapse, and big omega here is the longitude of the sending node. And these particles store symbolic expressions for the canonically conjugate coordinate momentum pairs. So this QP pairs list stored as an attribute, and it just lists all the pairs of canonically conjugate momentum, or coordinates and momentum for the Hamiltonian formulation of the problem. So in addition to storing these symbolic representations of all these variables, it also carries along numerical values of the different variables, and these numerical values were inherited directly from the rebound simulation that we used to initialize everything with. So here I'm just getting a symbolic expression for this momentum lambda 1, and to access its numerical values, I can pass the symbol as an argument to this dictionary attribute carried around by the particles. It's just to show that it stores the numerical value. It's sort of carried along with the symbolic stuff. You can also get things like masses and orbital elements, which are a little more natural to work with than these canonical variables. So in particular, these individual, so the G gravitational constant is stored, also inherited from the rebound simulation, and then individual particles represent the different planets, and they have, for example, you can get the semi-major axis, or the mass ratio with the star. So here what I've done on this bottom line is just recreate the definition of lambda, but using the orbital elements and these other parameters, just to show that you get the same numerical value. So you can see, this expression in the code matches the definition here for lambda. Okay, so that's the Poincare class, and now the other celmech class that we created when initializing our model was this Poincare Hamiltonian. And so this is designed to sort of capture the system's Hamiltonian that will govern the dynamics of the planet that you're interested in looking at. And so upon initialization, it stores a symbolic Hamiltonian that is initially just the Keplerian Hamiltonian. See, this didn't evaluate, right? So let me just jump over here and see. Right. So the attribute upon initialization is just a symbolic representation in terms of canonical variables for what is in terms of orbital elements, just the orbital Keplerian orbital energies of the pairs of planets. I don't know. might have to try remaking the slides real quick because it looks like for some reason all the outputs dropped. So let me just quickly. There we go. Sorry about that. There we go. Okay, so in addition to this symbolic representation of the Hamiltonian, so these things like G and these mass-related parameters carry around numerical values that are sort of stored internally by the Hamiltonian. So it knows, so you can see the Hamiltonian with numerical values of parameters substituted by accessing this n sub h attribute, for example. Let me just, okay. And so the basic way that you can work with this Hamiltonian object is by selecting and adding individual disturbing function terms to the Hamiltonian. So there's a sort of extensive user interface for specifying exactly which sort of disturbing function terms you'd like to add. In this case, since we're looking at a pair of planets near 3-2 mean motion resonance, we'll start by just adding terms related to the 3-2 mean motion resonance, and we'll just keep things at first order eccentricity. So there's the lowest order disturbing function terms being added. And so after we call this method, the symbolic representation of the Hamiltonian that this object is storing gets updated to this new expression here, which is a bit busy, but it really is just in terms of orbital elements, this expression. So you can use this df attribute to see the equivalent expression sort of rewritten in terms of orbital elements. So these are people who've done this sort of thing before, sort of leading order, first order resonance terms, and you see these cosine arguments that go along with the 3-2 resonance. Okay, so in addition to developing symbolic representation for the Hamiltonian, you can use this Poincare Hamiltonian class to get equations in motion and then integrate those equations in motion. So the integration interface, the way you interact with particles, is designed to mirror that of rebound quite closely. So in this short cell here, I'm just setting up an integration loop over some times. So I'm going out to 500 periods with one of the inner particle, and I'll store the eccentricities of the particles in an array. And you can see that each time through the loop, I'm just calling, well, for rebound, I'm calling the dot integrate method, and then our Poincare Hamiltonian has a similar dot integrate method. And when you call this, it integrates the system to that time. All the particles' attributes are updated accordingly. Store, for example, say the eccentricity of the inner planets, or of the rebound simulation, and the celmech simulation. So go ahead and compare two models. You see you get fair agreement with direct in-body, despite the fact that we're integrating a much simpler looking system instead of the full in-body equations. We just have this Hamiltonian full cosine terms in it. Okay, but there's some disagreement between in-body and celmech, and so we can try adding higher order terms from the disturbing function to see if we can account for some of the disagreement and try to understand why we see different results. So now we'll make a more accurate celmech model. So we're just going to add secular terms, so we'll go to third order in eccentricities. That means we're going to add secular terms at second order and terms associated with the 3-2 mean motion resonance up to third order eccentricities. And so this is just a simple two-line process. There's a special method for adding secular terms. You can tell it the maximum order that you want things up to. And now when we're adding our 3-2 mean motion resonant terms, we just say max order 3. So this will give us terms of the third order. So just to get a sense of what's now included in our improved model, we have a lot more terms. So there's secular terms, like e squared. There's terms associated with the 6 to 4 mean motion resonance, since that's a harmonic of 3 to 2. You see these are second order in eccentricity. There's terms associated with the 9 to 6 mean motion resonance, again, third order in eccentricity, a third harmonic. And then there's also terms that come in at third order, but multiply cosine terms of the 3 to 2. Just a quick word on the notation, which can be a little bit busy. You notice all these C's in front of all the cosine terms with a lot of subscripts and superscripts. And the way the notation works is that the subscript here designates the particular cosine argument that this coefficient is associated with. So in this case, it's these two terms, the 9 and -6 here, describe the multiples, the factors multiplying the lambda values, and this -3 here indicates that it's -3 times omega of the outer planet. These superscripts, which on this in this case are all 0, designate additional powers in E, so it's, I think, a little bit more illuminating to look at a case where the superscripts are not 0. So, for example, this term here has a 1 in the superscript, which just designates that you have an extra factor of E squared multiplying the cosine term, or maybe this one's a little simpler to see. So there's 4 because there can be contributions from the inner and outer planet's eccentricities or inclinations. So you can look in detail in the documentation for exactly how all the superscripts are defined, but that's just a quick word on it for everybody who's sort of mystified by all the superscripts and subscripts. Obviously, these terms would be pretty tedious to add by hand, but you saw with celmech it was just a few lines of code to add all these terms to the serving function. And now you can integrate and compare the rebound and celmech models. See, you get much better agreement with all these higher order terms added in. Okay, so I was going to move on to a simpler model with canonical transformations, but I guess I'll pause first before going on and see if anybody has any questions.
Yeah, Sam, I would like to ask until which order we can add terms to the Hamiltonian. I mean, you showed until I think was third order. Can we add like higher orders?
Sure. Yeah. Let me just run a quick.
I think a better question will be: is there a numerical limit for the number of terms we add?
Yeah. No. There's no limit. At least the code doesn't impose one. The only limit, I guess, is a practical one.
Okay.
In the sense that, you know, if you ask for like a 100th ordered model, it's probably gonna take forever to evaluate all the. When it adds these terms, you know, there's who knows how many of those. Yeah. So like if you look at things like the work done by Jack Lascar and his group, when he adds secular terms up to, I think, 6th order for the solar system, he ends up with hundreds of thousands of terms. And I think, you know, if you were adding resonant terms, that would be even more. But yeah, so the only limitation is a practical one. And if you wanted just a particular individual term from the disturbing function that happened to be very high order, then it's no issue to add just a single cosine term. So everything I showed in that example added collections of terms, but you have some control over the sort of, you know, you have finer grained controls that you wanted just, say I wanted to add just this single term that goes like E cubed and multiplies this cosine. You know, you have the ability to do that as well. Or if you wanted to add just a single cosine term. So you have a lot of control over what you can add through lots of different options.
Okay.
Sure. Okay. I see that I'm, oh, go ahead.
No, it's okay.
Did you have a question?
No, I was just, it's okay.
Okay. Yeah, so I go on, I guess. So one of the drawbacks of the last example is that we had this relatively simple Hamiltonian, but our equations of motion involved all 12 variables. Of course, the inclination variables were sort of trivial since we didn't have any inclination terms, but even then, you'd still have, I guess, 8 variables to follow. So we can actually make a simpler model for the dynamics by implementing canonical transformations. So the basic idea here is to look for a canonical transformation from our current set of coordinates and momenta, which I'm just calling qi and pi here, to a new set of variables, where I'm calling the new coordinates phi and q, and the new momenta I and p. And we want this canonical transformation so that our new transformed Hamiltonian doesn't depend explicitly on the new coordinates phi. So if we can do that, then according to Hamilton's equations, we have that all the I variables will be conserved quantities since dh d is 0. And if we can do that, we can then consider a simpler system, fewer degrees of freedom. So if we've eliminated, say, if we find m constants of motion, then we've reduced our total degrees of freedom to n minus m, and follow a lower degree of freedom system to understand the dynamics of whatever we're looking at. So it's a little abstract, perhaps. I think looking at concretely what we can do in this case is helpful. So our present Hamiltonian depends just or on all the angular variables only through combinations like this. I think maybe I didn't say it here, but these gammas are just the negative of the longitude of perihelion. So these are sort of the standard resonant angles that one sees for, in this case, it's 3 to 2 mean motion resonance. So we'd like to make some new variables, which we'll call Q1 and Q2, will be these resonant angles, and then we'll have some ignorable coordinates, phi. So we can actually automate this canonical transformation process with a special class in celmech, just called canonical transformation. And we can implement this sort of linear transformation of angles with a special way of initializing that. So here we're going to set up a matrix that gives us the matrix that I just showed here. And I'm going to create some new symbols for the new variables that we're going to use. So I'm going to match the notation that I had on the last slide. You actually don't have to explicitly create new symbols when you do this. If you don't, celmech will pick some default symbols to use for the new variables. But anyway, to get this new canonical transformation object, I just pass it the old state, our transformation matrix, and here is this, in this keyword argument, I'm telling it what I want the new variable symbols to use are. And so this canonical transformation has methods for transforming back and forth between old and new expressions, or expressions involving old and new variables. So in particular, it has a method called new to old that'll just, if you pass it an expression in terms of new variables, it'll transform that expression to the same thing in terms of the original variables. And so here I'm looping over all the new angle variables. So these were just defined here. These are the new symbols. And I loop through it just showing the new symbol and its corresponding expression in terms of old variables. variables. So these first two are resonant angles, and these other things are going to be orbital coordinates. In addition to transforming expressions, these canonical transformations have methods for transforming Hamiltonians themselves. So if I call this method, it'll return a new Hamiltonian object that's been transformed. And because I've used this do reduction keyword argument, it tells the transformation that it should reduce the number of degrees of freedom in the transformed Hamiltonian by just seeing which new variables don't appear explicitly in the transformed Hamiltonian. And it'll automatically determine what the conserved quantities are. And so now our new transformed Hamiltonian is a dynamical system in just these 4 variables instead of a full set of 12 variables that we started with. So this didn't fit on a single page, but the transformed Hamiltonian is now expressed in terms of the old variables. I'll just show the full expression over here. So you get a sense. So here you can see everything is written in terms of the new variables. Something to note is that the new conserved quantities, I1 and I2, do appear explicitly in the expression for the Hamiltonian. But rather than appearing as dynamical variables, they've been converted to parameters, meaning they basically have the same role that things like G and the masses and these coefficient values have. So it knows the numerical values of them, but it also puts them in as an expression. Okay, like I said, you can automatically identify conserved quantities. The transform Hamiltonian knows that it's been reduced from a sort of higher dimensional system, and it carries along with it, in addition to the sort of active dynamical variables, it has this attribute called full QP vars, which tracks the full dimensional phase space. And so here I'm assigning the momentum variables of the full phase space to this list full P's, and then just the dynamical variable ones to this new list. And if I loop through, I'm showing for each momentum in the full phase space that's not a dynamical variable, I'm just showing the expression for it in terms of the old variables, and this is a just nice way of displaying the conserved quantities. So you might recognize this first one here as the total angular momentum, at least for coplanar planets. The second conserved quantity is related to the fact that the system's only in a 3:2, or is in a 3:2 resonance, and only terms involving the 3:2 resonance appear in the Hamiltonian, and these last two just reflect the conservation of inclination since the system's coplanar. Okay, so we could take this new Hamiltonian and just integrate the equations of motion like we did before, and we could get a similar time evolution of the trajectories. But now we'll look at a different application. In this case, we're going to look for a resonant equilibrium configuration. That is a configuration where our new momentum and coordinate variables are fixed. And then once we find this configuration, we can transform back using all the canonical transformations that we made, and we'll do that and produce a rebound simulation that's at the resonant equilibrium. So before determining the equilibrium configuration, we're actually going to do one more canonical transformation to these new variables x and y, which are related to the p's and q's in a sort of polar to Cartesian way, or transformation. And the reason for this is because it's numerically easier often to find roots in terms of these variables than it is the p's and q's. So again, we can use this canonical transformation object. This constructor here is sort of designed as a convenience method for getting this canonical transformation from the polar style variables to Cartesian ones. You tell it the full set of variables that you're transforming from, as well as the indices of the variables that you want converted to Cartesian style coordinates. And we've produced this new Hamiltonian in terms of the new x and y variables instead of the p's and q's. Again, the Hamiltonian expression is rewritten in terms of the x's and y's. This is just a long mess of x's and y's, but illustrates the point. And so now, in order to find the equilibrium configuration, we're going to solve for where our flow is 0. In other words, we're going to use this function, this flow function, that returns the sort of vector of derivatives according to Hamilton's equations for our coordinates and momenta. And we can also use the Jacobian of this function, which is stored as an attribute of the Hamiltonian. And that just gives the Jacobian matrix derived from this vector function. And we can use a sort of generic root finding method like scipy's optimized.root to find the point where this flow vector is 0. And so in this cell here, I'm defining this f. I'm using this sort of lambda function construction just to put it in the form taken by this root function. Same thing for df here. And I'm just passing the root function an initial guess for the root of this function, the Jacobian, and it solves the root for me, and I can store these values in this variable yx star. So I'm solving using root to solve for these values that satisfy this condition. Now that I have this condition, I can update the state of the system, and just to confirm that it's actually close to the equilibrium after I've reset the state, I've just called the calculate flow, which returns the numerical value for this f at the current state of the system, and you see that it's essentially 0 to within whatever tolerance I gave the root binding. Okay. And so I said we want to take this root that we found in our new transform variables and go back to our original variables so that we can get a rebound simulation at this equilibrium. So in order to do that, recall that we've done 2 canonical transformations so far. The first one to those p and q variables, and then from the p and q to these new x and y variables. So in order to go back, we're going to make a transformation that's the composition of those 2 transformations. And so there's this composite constructor where you just pass a list of canonical transformations and it automatically generates the transformation that's the composition of the 2. And so I'm just showing the old variables of this composite transformation and the new variables that it transforms to. And these are, remember, we found x's and y's that are corresponding to the resonant equilibrium. Okay, so we can apply our transformation, or really the inverse transformation, to go from the equilibrium that we found and rewrite it in terms of old variable values. So I'm getting the equilibrium values here. Note that I'm using this full values attribute rather than just values, because our full phase space is actually 12-dimensional and not the 4-dimensional reduced phase space. That's what's required by the canonical transformation. So anyway, I get the old values, I create a new Poincare object and set its canonical variables to these values, and then use that to quickly initialize a rebound simulation. And you can, I've hidden some code here, but basically taking this rebound simulation and integrating it forward in time, see that I've plotted Q1 and Q2, these resonant angles, see that they sit at the equilibrium values of 0 and 180, whereas our initial rebound simulation that we started with evolves along this red trajectory, so it's away from the equilibrium value. Okay. So that's sort of the end of this canonical transformation example. If anyone has any questions about that, happy to answer them. Otherwise, I can go on to the next example.
Just to be sure, the main role of celmech in this problem will be just to provide the equilibrium configuration, so then you can run on rebound, right? So you get the problem,
Yeah.
you make the transformations, you get the equilibrium configuration you need, and then you go back to rebound, and then you simulate.
Yeah, right. Or I guess if for some reason you needed an in-body simulation at equilibrium,
Yes.
you know, if I had integrated this example in celmech itself, it would have sort of trivially, you would have trivially not gotten any evolution since you had already found the sort of fixed points of its the differential equation that it's solving. Yeah, I guess this last little bit here is to just demonstrate that it really did find the equilibrium configuration.
Okay.
Yeah, there's something. Okay, so I did. There's a subtlety here, and that it found an equal. Okay, I won't go back, but remember, there's actually a whole family of equilibrium configurations, and the one that and those are set by the values of those conserved quantities I1 and I2. And so if the values of I1 and I2 had been different, it would have found a different equilibrium configuration. So if you're interested in finding a bunch of different equilibrium configurations, you can actually go in, and every time you numerically change the value of I1 and I2, that'll be sort of carried over to the equations of motion that celmech is working with, and so you can sort of solve for the whole family of equilibria. I think there's some examples, the Jupyter examples, sort of demonstrating that process.
Okay. So, and another question. So you can integrate everything on celmech. You don't have to go back exactly to rebound. You can do on celmech.
That's right. Yeah. In this case, I just did it to illustrate that it had really done what it, you know, if it did a bad job of finding the equilibrium, then you would have seen the n-body be a little bit, or be sort of not this close to equilibrium. If I really zoomed in on these black curves, you would see some high frequency terms, so some high frequency oscillations, and that has to do with the fact that in our celmech model, we're only keeping a finite number of cosine terms in our approximation of the interaction potential, but in reality, you know, there's an infinite set, and so most of those other ones are sort of rapidly oscillating, and so they don't have a big effect on the dynamics. But you would be able to see them if you zoomed in here on the n-body, that is, rather. Yeah, in this case, integrating the celmech model would sort of do, it would just sit at the fixed point and sort of do nothing.
Okay, sure, thanks.
Yep. Okay, so this brings me to another example. So this co-orbital resonances. So Ricardo suggested that either he or somebody else was interested in seeing an application to co-orbital resonances. And as I was making this, I realized it's actually quite a nice example because it illustrates doing something sort of non-standard with celmech, and it sort of illustrates sort of how it works under the hood a little bit. Because in this case, we're going to make a custom Hamiltonian. But backing up a little bit, anyway, co-orbital resonance occurs basically for planets with essentially equal semi-major axes. As the name suggests, they're on the same orbit, more or less. And so I'm setting up in this example a rebound simulation with a couple of equal mass planets with equal semi-major axes. Setting their semi-major axes to 1, and I'm just having the second planet lead the first planet by 80 degrees in its orbit. 60 degrees is a fixed point where the things would just go around in a fixed triangle, essentially. And so with this setup, we expect some motion around that equilibrium configuration. And indeed, if you look at the time evolution of the system, you can see that co-orbital resonance is characterized by the libration of this angle, this synodic angle, psi, which is just the difference in mean longitudes, rather. So I'm plotting just the time evolution for that system. You can see psi oscillates back and forth around this equilibrium value of 60 degrees or minus 60 degrees in this case. And along with those oscillations in psi, you get oscillations in the two planets' semi-major axes, and these are 180 degrees out of phase. It's basically dictated by conservation of energy for the system. Okay, so if you wanted to do this the way we've seen things done so far with celmech, by adding disturbing function terms, you would quickly find out that the disturbing function expansion and the corresponding coefficients appearing in a diverge for alpha equals 1, or when the semi-major axis ratio of the two planets is unity. So you can't treat this problem by a classical disturbing function expansion, since the planets are co-orbital, but we'll still use celmech by creating our own custom terms to add to the Hamiltonian using SymPy. And for simplicity, we'll just keep things at 0th order in the eccentricities and inclinations. You can see, for example, this reference or some others in the literature for how this can be developed to higher order in eccentricities and inclinations. But anyway, I start out by just initializing this Poincare object and the corresponding Hamiltonian object. From that, I'm getting out just some symbols that I need to construct the expression for the interaction potential. And I've created some symbols to represent the planet's semi-major axes, and I've also extracted the symbols for the planet's mean longitudes. So I can just construct this symbolic expression, which I'm calling phi 0. So this first term here is just the gravitational potential for a pair of planets on a circular orbit, or on circular orbits. This last term here is an indirect term, basically arising from the fact that we're working in a non-inertial coordinate system. And so we've expressed this potential term in terms of orbital elements, but in order to use it in celmech, we need to express it in terms of our canonical variables. And so in order to do that, just define a substitution rule, which I've done here. Basically, I've re-expressed the semi-major axes in terms of these canonical momenta lambda. So these are the appropriate expressions for the semi-major axis in terms of lambda. And SymPy has this, every SymPy expression has this method called subs, where it just applies some substitution rule. And so this is just the potential that I had before, but now with these expressions substituted for the semi-major axes. And so I can add this interaction potential term to the Hamiltonian, symbolic Hamiltonian stored by our PHAM object here. And once I add this expression to it, it automatically updates all the properties of the Hamiltonian. So for example, I'm just showing that the time derivative of lambda 1 is updated after I've added this symbolic expression. So this inflow contains all the time derivatives, and the sixth one corresponds to one. So this is just a symbolic expression for the new time derivative. So the equations of motion are updated automatically. Again, we can integrate this Hamiltonian just like we have before. And if we compare it with n-body, we can see that we match body evolution very well. So this is just a simple 0th order eccentricity inclination model, and it does quite a good job of matching the direct n-body model. we can actually do a canonical transformation, similar to the ones we've done before, and turn this into a 1 degree of freedom system. So if we make one of our new variables just the synodic angle, we can get a corresponding conjugate momentum that's just the difference between the planet's lambdas. And we have a single degree of freedom Hamiltonian. So I'm doing this using the same angle transformation matrix that I've showed in the last example. In this case, it's much simpler than some of the other ones. But we've rewritten everything, and you can see that when I get the symbolic expression for the new Hamiltonian, the only variables that appear are this P1 and Q1. Lots of sort of funny looking numbers. But anyway, you can now use this 1 degree of freedom Hamiltonian to make contours of constant energy. And so these are, since it's a 1 degree of freedom system, you can sort of plot out all the trajectories. So each trajectory on this plane here is a trajectory for a different energy. So I've just made a grid inside our angle variable and the momentum variable, and use Matplotlib's contour function to make this figure here. You can see that the stable equilibrium points set at plus and minus 60 degrees. It's a variable, and there's actually an unstable point at 182, which corresponds to the one of the Lagrange points. I think it's L3. Okay, we can actually use our canonical transformation too to get the values of Q1 and P1 directly from n-body. So we can compare n-body directly to our analytic model in this case. Actually, the expressions for Q1 and P1 in terms of orbital elements are pretty simple in this case, but I think this is illustrative for, there might not always be in other applications, so it's nice to see that you can, so I'm looping here through the, over time, integrating the simulation, and each step through the loop, I'm creating one of these Poincare objects out of our simulation, and then applying our canonical transformation to that object to get values of our new coordinates, and I'm just storing them each time through the loop. So I'm getting Q1 and P1 directly from n-body at each step through the loop. And you can compare the n-body trajectory to this simple 1 degree of freedom model by plotting the trajectory on the same plane of P1 versus Q1. You can see that it follows the contours quite nicely. So this simple 1 degree of freedom model, it gives a quite nice model for the n-body evolution. Okay, so I'm coming up on an hour. I did put together a quick example on 3-body resonance, but in the interest of time, maybe I'll just pause and see if anybody has any questions. And just say that you can check out this example in this notebook itself, and there's actually a more extended example of analyzing actually 4-body resonant chain on GitHub. So this one that I've put in this notebook is designed to apply to model the Galilean satellites, and this one on GitHub looks at a particular Kepler system that's a resonant chain of 4 planets. So I think I'll leave it at that and see if anybody has any questions.
I don't think there is any question at the moment. Well, I'd like to ask, but at the end, just at the end, so you can keep on.
Oh, okay. Well, I can go quickly through this 3-body resonance
Yes,
example.
please. Please.
Okay, sure. Okay, yeah. So here I'm setting up a system that's roughly equivalent to the orbits of Io, Europa, and Ganymede around Jupiter. So this is just initializing the rebound simulation. This is the plot you get. You set it up, and now I'm going to add a bunch of disturbing function terms similar to what we've done the first example. I think this is a little more illustrative of what you do when you need, you have more than 2 planets. Add lots of different terms. So I'm taking the rebound simulation and turning that into this Poincare Hamiltonian object that I'm calling P-Han Galilean. And here I'm going to work up to 3rd order in the eccentricities. And so in these couple lines here, I'm adding 2-to-1 terms between adjacent satellites. And I specify which pair of satellites I'm adding things between with these index in and index out keyword arguments. And I'm also adding a 4-to-1 resonance. Since they're in a 1 to 2 to 4, there's a 4-to-1 resonance between Io and Europa. And so the way you specify that is the first number here specifies 4, and this last number here actually specifies the order. So 4-to-1, 1 is 4 minus 3, basically, is why there's a 3 here. Again, I'm saying index in and index out are 1 and 3. And then I'm also adding pairwise secular terms between each pair of planets in this double loop here. So it adds each pairwise set of secular terms to 2nd order eccentricity. So in this example, there's actually a subtlety that I found. To get good agreement with n-body, you actually have to correct from the osculating elements of the full n-body problem to the mean elements that are more appropriate for the analytic model. I spoke a little bit about these earlier, but effectively what you have to do is remove rapidly oscillating terms from the initial conditions. I'm not going to sort of belabor this because it would sort of take us away from the main example, but you can see the documentation. Try to do this in more details, but basically the workhorse for this sort of thing is this 1st order generating function object, which is under CELMech LB transformations. So you can add some corrections, and then you just call oscillating to mean. That'll correct for rapidly oscillating terms that you've told it to. Okay, and so in this cell here, I'm setting up a canonical transformation. It's not strictly necessary. I could just integrate the model I have, but here I'm transforming to this Q1, which is the sort of 3-body resonant angle, and then I'm also, I think the notation got a little messed up. That's supposed to be 2 lambda 3 minus lambda 2, bearing on the cosine arguments here. But I'm doing this again with this from Poincare angles matrix first, and then applying this polar to Cartesian transformation here at the end. Applying all the same things I did before, so I'm setting up this matrix to define what our new angles are going to be, and then transforming from some polar to Cartesian stuff to get a final formula for the Hamiltonian, integrating again by looping over time, here integrating both the rebound simulation and the new Hamiltonian that I've created, and saving this 3-body resonant angle in the loop, and then plotting the comparison. It actually pretty good agreement between n-body and CELMech. Of course, a more realistic model could include things like other moons of Jupiter and the quadrupole moment of Jupiter as well, and some inclinations. So imagine making an arbitrarily elaborate model that way. But yeah, that's sort of brings me to the end of my examples. So yeah, I'll stop there.
Okay. So in general, so you can, it's very practical. So you may have a 2-body resonance, and for instance, a 3rd body that has a secular relevant perturbation. You can just consider this in the Hamiltonian, including this secular perturbation, and follows.
Yeah, that's right. So if you had, for example, a system where one pair of planets was in resonance, and then there may be like a distant perturber, say, at resonant interactions between the resonant planets and then just the secular contribution from the distant one. It's sort of, often part of figuring out what you need. Often part of the problem is just figuring out what you need to include to sort of capture the relevant dynamics, and that's where sort of close interface with rebound helps, where you can try some setup in rebound, integrate it, and then see what you need. If you're developing some analytic model, you can see what terms do I need to get adequate agreement with in-body, and then once you sort of have your minimal model working, you can analyze that whatever way.
Okay. So it's great. I think it's a wonderful tool to make this analysis. It's very good, very good. And the example you showed of orbitals, so you can introduce some other models in the Hamiltonian as you wish. So
yeah, that's right. And in fact, let me go back. Yeah. So yeah, any basically, this is like I said earlier. It's all sort of built around SymPy, which is this library, which is where I'm getting all these, these nice typeset symbolic expressions that are all sort of done by SymPy under the hood. So these symbolic expressions are basically direct output from SymPy. So if you can formulate some sort of symbolic expression, you can just add it to the Hamiltonian that you're interested in. Or even more generally, if you just want to come up with, if you have some Hamiltonian model in mind and say it doesn't even have anything to do with celestial mechanics necessarily. This example is on the documentation and on the GitHub examples, but if you just wanted to integrate a pendulum, for example, this is pretty basic, but you can set it up by, so here's all the code for doing it. I'm just creating, I make these symbols with SymPy, I make a symbolic expression for the Hamiltonian. There's a couple other steps in initializing this sort of generic Hamiltonian state. So this Poincare Hamiltonian that I used for most of the celestial mechanics examples is just a special instance of this more generic Hamiltonian that can sort of accept anything. So this object basically automatically generates your equations of motion and stuff. And I'm here doing
so you can
something.
include, for instance, the gravitational term of the central body if you include some other terms.
That's right. Yeah, and in fact, there is a function for adding the like J2 contribution. But if you had something more elaborate, say I haven't implemented J4, but if you wanted to do it by hand, you could certainly like put in a potential term representing J4 or some other effect. And if you want to include non-conservative forces, for example, you can
Radiation pressure.
Yeah, say radiation pressure. You can use celmech to generate the conservative part of the equations, and then you can just define a new set of equations that's the sum of the conservative equations generated by celmech plus whatever dissipative part of the flow, the ODEs you want to add to it. So that's, I think, that I've certainly used it for, like adding just sort of eccentricity damping and migration forces, for example. But imagine doing it with radiation forces as well.
Yes. Okay. Great. That's great. So we are open for a question. Anybody else would like to make a question or a comment, please? I think you were very, very clear in your explanation. I think the main thing to do is hands-on. We have to work on it. Perhaps some doubts may appear later, but at this moment, I think it's very clear. I think it's hands-on.
Yeah. Well, I hope it's my understanding that most people have a dynamics background, so I hope I didn't lose anybody. But yeah, like I said, you can check it out on GitHub if you. I'm also, if you make some part of it that, if you make some modification that you think other people might be interested in, you can submit for the community contributions through GitHub as well. So.
Good. So you can increase the library. That's good.
Yeah. We try to be responsive to any, if you run into issues or bugs or anything, let us know. You're certainly not the only one if you find something. So yeah, well, thanks for having me.
Okay, so it was great. Thanks very much. I think it was very useful. I think some of us are going to watch this again and implement and try to
yeah. Feel free to reach out with any questions.
Okay, good.
Right.
So thanks very much for the presentation, and it's a very interesting work, and I think it's going to be very, very useful, this too. Thank you.
Great.
Okay.